Hey, this is Brock Lemires, and in this video we're going to continue talking about AC signals and specifically the electrical characteristics of a sine wave. What I mean by that is the electrical parameters that are of interest to electrical engineers when we look at AC signals that are modeled by a sine wave. Okay, so we've already kind of looked at how the sine wave is used to model a lot of different phenomena that occur in electrical engineering. And probably the two most common are going to be the signals that you get out of an electric generator. So the currents and the voltage are going to vary with time just due to the way that generators are constructed with a rotational, motion that results in moving wires or moving charge through a magnetic field. And what happens is that the wave shape that you get out of that is a sine wave. The other kind of big component of electrical engineering that uses sine waves are electromagnetic radiation. So all of the propagating waves that we use for radio and Wi-Fi and light and x-rays, we model those as little packets of sinusoids. Okay, so we use the sine wave function in all the math that we use to describe what's happening. So let's begin by defining some of the characteristics of the sine function that we care about in electrical engineering. So if I go ahead and draw the kind of the standard sine wave, so I just have one cycle of this thing. Let's see, so it goes up and goes down, and there you go. All right. One of the first things you realize is that the sine function itself is kind of this mathematical function that's been defined that can be applied to a lot of different applications. And so when you look at it for the first time, you can kind of remember some of the things that happened. For example, one cycle of the sine wave goes from 0 to 2 pi when you write it like this: y is equal to sine x. So 2 pi is when this sine wave will repeat. And then also this function, basically you go from positive 1 to negative 1 in terms of what the peak value of this function is, and negative 1 as the kind of the peak negative value that you get. But electrical engineers need to kind of translate the math definition of the sine into something more useful. So let's begin first and foremost. We are not talking x and y anymore. What we are almost always doing is talking about some electrical quantity versus time. And so the electrical quantity, we know that it's usually voltage or current. So let's just do an arbitrary kind of voltage to start off with. One of the things you'll notice right away is that when you write the sine function that varies with time, the terminology is you switch to a lowercase v. Okay, and so then when I look at that lowercase v instead of the uppercase v, that means, oh, this is an AC signal that is a function of time, or is a function of something, in this case of time. And so this is kind of the uppercase is used for DC or constant values, and then the lowercase is used for functions that vary. Okay, so then when I write out this equation now I'm at sine of t. And I haven't done any scaling to this yet to make it fit, so it still kind of goes between 0 and 2 pi and from 1 to negative 1, but we'll look at that in a minute. Let's define a couple of things that we care about. So first and foremost, the period is what we call, or period is the amount of time that it takes for one cycle to complete. Okay, and we give this the capital letter T. Okay, so that is the period of the sine wave, and the units of period are going to be seconds. Okay, and this is obvious that this is an important thing. If we're going to have something that repeats, don't you want to know how long it takes for it to repeat? And it's absolutely, okay, it's period. Okay, then we can immediately flip that into something that is called the frequency. Okay, and the frequency is going to be the number of cycles that occur per second. So this is the number of cycles, okay, per second. So if this thing goes one full cycle in 1 second, the frequency is 1. If it does 2 full cycles in 1 second, it's going to be 2. So that's frequency, and we give this a unit called Hertz. So this is the frequency that we use in electrical engineering. It's Hertz. And you go, where did Hertz come from? Well, it's some dude, right? Some mathematician, some scientist that was credited with some discovery in electrical engineering or physics related to physics, some discovery in physics that's related to electrical engineering, and so he was honored by giving his name to Hertz. And so it's capital H, lowercase z. So that's Hertz. And the frequency and the period are they are related by F is equal to 1 over T. Okay, so once you know one or the other, you know you know the other one. Okay, and frequency is lowercase f, and then period is uppercase T. Okay, so there's one last kind of time component to the sine wave, and that is called phase. So phase of a single sine wave represents how much to the right or to the left the sine wave has been shifted from its base location. So its base location is basically at t equals 0, the sine wave function is going to result in 0, and it'll start here and then it'll go up. But we can absolutely have signals that are shifted left or right, and we call that the phase. Okay, and we'll talk about phase a lot because there's not just only phase of the sine wave itself, which represents how much it is shifted from t equals 0, but we'll also use it when we compare multiple sine waves in a circuit, and we'll say what is the phase difference between sinusoid A and sinusoid B. And then of course the phase can take on a negative or a positive value depending on whether you shift it left or whether you shift it right. Now let's take a look at the voltage, some of the parameters of the voltage. So first and foremost, we're going to have a value that is going to be called the peak voltage or the amplitude. Okay, so this right here is going to be the amplitude, or the V peak. Okay. And we can do that when you use amplitude, you typically give it like a subscript. So I can say like V1 or like V0, and then when you do V peak, you usually do like VPK. Okay, and obviously when you do this, this right here on the voltage axis is going to be V peak right here, and then this down here will be negative V peak. Okay, and so that's the amplitude. And then another thing that we talk about is the peak to peak voltage. So if you come out here, I'll draw it over here to be a little bit different. So then right over here is going to be the V peak to peak V peak to peak voltage right there. And obviously this is going to be equal to 2 times V peak. So these are two things that we care about when we talk about the size of a sine wave. Okay. Another really common thing that we talk about is the RMS voltage of a sine wave. And what RMS is, it's the average voltage magnitude. Okay, and it's a little weird because you can't really take the average of a sine wave by itself, because if you think about it, if I summed up all these values and then divided it by the amount of time, the value of the average would be 0, because the part that's positive is equal to the part that's negative, and so it's really meaningless. But we do for sure know that there's energy and magnitude associated with this sine wave. So in general, you're probably going to have it land somewhere in there. And where this comes from is RMS is a technique that you can apply to a waveform in order to find its average value. I mean, there's no way around it. So let's take a look at what it actually is. So RMS equals root mean square. Okay. And you basically are taking the square root of the average of the square of a waveform. Okay, and so here's kind of the way this works. Let's work backwards. So what you're going to do is you're going to square the sine wave. And so if I square that sine wave, what I end up with is the negative times a negative results in a positive. So you're going to have something that kind of looks more like this. Okay. So you're going to have 2 humps like that. So that's the square part of it. Then if you take the mean of it, what that's going to do is now you can actually take an average value of this that will be positive. So you're going to get some value on there that is representative of, basically somewhere in the middle of here that represents that's about the magnitude of it. And that's the mean part of it. And then the root of that, so then you're going to take this value right here and you're going to do the square root of it. And what that does is it compensates for the squared that you did before. So if you had something that was like 7 and you squared it, it'd be 49. Well, you got to get it back down to the original kind of magnitudes. You have to root it. Okay. So that's root mean square. So if you had that graphically, you could plot this out and you could actually do all this mathematically. But it turns out that VRMS can also be found by taking V peak and dividing it by the square root of 2. Okay, and the square root of 2, you'll find this a lot in electrical engineering and kind of scientific math. Square root of 2 is like 1.41, and if you take 1 over the square root of 2, that comes out to be 0.7, 7 something. And if you think about that, if you take the V peak, if V peak was 1 in this example, and you divided it by 1.41, what you're doing is multiplying it by about 0.7. So this tends to be somewhere around 70%, but it doesn't really matter. The equation that we always use in engineering is V peak over the square root of 2. Now, here's what's interesting about RMS voltage. If somebody walks up to you and says, I've got 120 volts, if they don't say anything, okay, so if they don't specify, okay, and I mean don't specify as in they don't say the peak voltage of this signal is this, or the peak to peak voltage is this. If they just say I have an AC voltage and its number is 120, they're always talking about RMS. So that's kind of the way that we speak. If you don't specify it, it's RMS. So it's don't specify means RMS. In electricity, that's the way that we talk. So for example, your outlet is AC voltage on there, and it's the voltage that comes out of your outlet is between 110 and 120 volts. But that voltage, since we never specify whether it's amplitude, peak to peak, etc., it's always RMS. So when someone says that I have 110 volts in my outlet, they're talking about RMS. And you could certainly convert that back to peak if you wanted to see how actually big the sine wave is coming out of your wall. But that's what RMS is, okay? So RMS is used heavily in the electrical power industry, because that's the way our electrical grid operates. It's all RMS. And it's pretty cool because all of the rules for circuit analysis and Ohm's law, they all work on any of these values. So peak to peak, peak, or RMS. And so you can still do Ohm's law, and you can do Kirchhoff's current law and voltage law and all that sort of stuff. Okay, so there's one last characteristic of a sine wave that we do use, and it is certainly possible for an electrical signal to not be centered at 0. So notice that everything that we've drawn so far has been, it's centered around 0, because that's the way that the sine wave, the base sine wave works. But it doesn't have to be. I mean, you could certainly have like a plot where you have time and you have 0 volts over here, and this is V of t, and the sine wave is sitting like up somewhere. So it's like it's centered around some line. So it's like doing this sort of thing. And that's perfectly legal. I mean, if that happens, we need to model it. And what we do is we call this the DC offset. Okay, so it is just a fixed voltage that you add to the sine wave, and it will shift it up. And you can obviously subtract it too to shift it down, but this is going to be called your V offset, and that basically allows you to basically move this thing up and down. Note one thing about it, that the peak voltage or the amplitude still swings around this offset, okay, because it used to swing around 0, but now it's just going to shift around this new offset that we've applied to it. Okay, so that concludes all the parameters we're going to cover. So the next step is figuring out how we plug those characteristics into the base function of a sine wave, but we'll do that in the next video. That's it, and see ya.